imaging, which I hope was useful to all of you. And so today I would like to go on with this, how to say, more experimental part. So I will recall some basic features of synthetic aperture radar imaging. And then I would like to present you some simulations concerning both the simulation of some effect that show up in some images, as well as if we have time, so I'm not sure, a focusing scheme for a synthetic aperture radar system. So, just to recall the basics of array imaging, we say that we have an array so we have a fixed array of some length transmitting some bandwidth B, and then you know that resolution is given in range by the inverse of the bandwidth, and then you have an angular resolution which depends on the inverse of this length. And so, with a system of this kind, you can focus along different angles.
What is next to the error?
And so you have angular resolution, and let's say this is your ROPC, and a range resolution. This is your ROR. So a fixed angular resolution. This means that if you have a single target, this will show up as a product of two cardinal signs, so one in range and one in azimuth, as long as you form an image in the range and angular domain. Of course, if you project this image in a Cartesian space, like we did last Thursday, then you have a different point response, and in particular the linear resolution of your target, so your capability to resolve target in a different position. So let's say that this is x. So this coordinate here is x. Then your resolution along this x coordinate is more or less given by the angular resolution times the range. So the closer you are to your array, and the finer is your linear resolution. And this is why your angular resolution is fixed with a system of this kind. Okay, so you can focus at different angles with a fixed angular resolution, with an array, with a fixed array. Now, we go to a SAR system. So a SAR system is a radar that is flown on board some platform. Let's say that this is the x coordinate. We call this azimuth. So strictly speaking, azimuth is an angle. So this C angle is called azimuth, but in the SAR jargon, we just call this azimuth as well. So just for it. And we have a radar that is transmitting and receiving as it is flown over this trajectory. So the trick to understand synthetic aperture radar is to see that if you take, well, of course, as you are transmitting and receiving, you are also storing your data in a matrix, which is called the data matrix. So let's say if this is x, so you have your different x position, then you have a time signal for each position. So exactly as we saw last time. So if you just cut a series of rows here, so let's say that you cut this data here, then it means that you are only considering a portion of your trajectory, let's say from here to here, which means that it is which means that what you have is you have the same signal which you would have using a fixed array at this position. So it's easy at the end. So we say so what are the resolution of a SAR image? So we say that it is analogous to a fixed array. So you have the same range resolution and the same angular resolution, and so the same x resolution, azimuth resolution. Of course, the question is how long is the synthetic aperture? A. Take care, because the question is so the answer changes with the distance of the target from your trajectory. So for example, if your target is here, then your synthetic aperture is short, because this target is only illuminated, let's say from here to here. If your target is like far away from your trajectory, then this is your synthetic aperture. It is much larger. And you can easily compute this synthetic aperture. So assume that you are flying an antenna whose physical length is L. So this is the physical length of your antenna. Then you know that this antenna will emit over an angular sector, let's call it delta psi, which is equal to lambda divided by L. And so the beam width at the distance of the target is, so this one, this is R. So A is equal to delta psi times R. So for a synthetic aperture radar system, the antenna, the array aperture, well, in the first place, it moves, it slides. And in the second place, it is also larger or shorter depending on the distance of your target from your trajectory. So these two are two very important differences. But if you understand that, then the resolution is easy. So we say that this is your angular resolution, so let's plug this expression in here. And you get this expression. And so your angular resolution now depends on the range. Go back to your linear resolution. then you get this expression, which does not depend on range any longer. So a SAS system has a fixed linear resolution. Big difference. And you can also specify this one. What you get is that for a SAS system, your azimuth resolution is equal to half the physical length of your antenna, which is the paradox of synthetic aperture radars. This is all on the slide, so this is more or less it. A reminder. So, fixed azimuth resolution. Another, well, let's see. Fixed azimuth resolution. So this means that you can write the pulse response of a SAR system very easily in the range and azimuth domain. So just imagine that you produce an image. So let's say this is range and this is x. Then a target will show up as a bright point here. And this bright point can be written as cardinal sign of r minus r0 divided by the range resolution. Cardinal sign of x minus x0 divided by the azimuth. So you see that a SAR system is also providing us with a nice feature. So it naturally produces images in a coordinate system which is closer to what we would like to see. So it is not yet a Cartesian coordinate system, so it is not yet a UTM or let's say a coordinate system that we can use right away, but it is closer to what we would like to see, to our experience, I mean, to the way we do perceive things. Yeah.
But what exactly is this expression? What does it mean?
Oh, this is an image. This is
No,
the
no.
mathematical expression of a SAR image when you have just one target at the distance r0 from the trajectory and at x coordinate x0.
Ah, okay.
It is the pulse response of your system. Okay. So a thing that is relevant to say is that so I will not talk about focusing now. If I have time, I will do it at the end of this lecture. But what is relevant to see here is that there is yet another difference with the case of a fixed array, which is that imagine that you are just cutting the data here. And so you are just taking a portion of your trajectory. So if this were a fixed array, then you would use this data to focus the target at all angles. So with the fixed array, you produce an image because you focus the target. You remember, no? You take the Fourier transform, which means that you get different spatial frequencies, and different spatial frequencies correspond to different angles. So the samples of the Fourier transform correspond to different angles here. Right. With the SAR, you don't need to do that, because imagine that you cut this portion of data here, and you use this data to compute the target just here. So on the let's say just to compute just to focus the target here, which means that you only focus for C equal to 0. You do not need to focus for different angles. Why? Because you have a sliding aperture. So you can just stay here and focus the target along this line. When you want to focus a target at this other position, you will simply take the subsequent portion of data. So from here to here. Okay. So let's say that in some sense star imaging is even easier, because you take a portion of data and you just focus perpendicularly to the trajectory. You don't need to compute the other angles, because you get this other target as you slide. So you slide and you just focus for C equal to 0. Okay. So this method, this approach to focusing is called zero Doppler focusing. Because if you take a certain portion of data, then the points that are along this line are said to be at zero Doppler with respect to the data. Okay. Now this is just radar jargon. I will not insist on a physical meaning, because I tell you there is no physical meaning here. They call this Doppler, but this is not Doppler. This is something else. And so I hope I'll be back on this later, just to explain you where this terminology comes from. But as a matter of fact, there is no Doppler, and you can see this in a very simple way. Just imagine that you have a system where you put your antenna here, transmit, receive, here, transmit, receive, transmit, receive. You form a SAR system, right? Yet there cannot be any Doppler involved, because as long as I'm still, as I transmit and receive, and I assume my targets are still as well, there is no velocity at all. So no velocity, no Doppler effect. Okay? So keep this in mind. It is called zero Doppler, but as a matter of let's take this now. So it is called Doppler because if I physically move, so imagine that I am focusing, I don't know, this point here. So this is my target. This is called Doppler because if I physically move as I am transmitting and receiving, then there is a relative velocity, a relative radial velocity between me and the target here. Now the radial velocity is diminishing, and here it is 0. There is no radial velocity at this position. And then here I have a negative radial velocity, meaning that we are getting far from the target. So for this reason, when I'm flying here and I see the target perpendicularly, this is at 0 Doppler. Okay, but as I said, you can as well imagine that you are still in air. You are just hovering in air as you are transmitting and receiving, and so there is no physical velocity involved. Okay, sorry for the diversion. So we were at the pulse response, right? So let's go back here.
Sorry.
Yeah.
I think that once you got the data matrix, so the data that I collect for the different movements of the data, I don't get how can I get the image without the FFT? But why should
No, wait. Let's say for the moment you do have an FFT, but you just save the central sample. You just save the sample that corresponds to 0 spatial frequency or 0 Doppler, and you throw away the other ones because you get the different. You do not need the different angles to get this other target because you will see this target at 0 Doppler when you're here.
So the point is that I have to understand when a target is 0 Doppler to, with respect to the position of my antenna.
It comes by itself. I have a code for that, so I think it's easier if you see a code directly. There's no need to understand. What you do at the end, you just do a convolution along X, and you get the focused image. But it will be better at this point. So be patient for the moment, because what is important for you to know now is how to have tools to understand a SR image. So first important thing, this expression is super important. This is the expression of a focused SAR data. You still do not know exactly how to focus, and this is beautiful. So you still do not know how to focus, but just by analyzing how the system is made, you know that the final focused image will have this formula. This is super powerful. Actually, I forgot here the phase, so I should also have put here. I should also have put here the expression of the phase. And now this is complete. So you have two very important things that follow after this expression. Let's say three. So the first thing is that if you are not interested in simulating the acquisition chain of a SAR system, You just want to simulate a SAR image after focusing. Here it is. If you have a single point, that is a SAR image. If you have multiple points, let's say that you have points that are already represented as a function of range and azimuth, then you get a SAR image by integrating that expression over range and azimuth. So your SAR image will be oops, I forgot the A, sorry. So A. There you go. So A represents the, let's say, the intensity of your target, which are represented as a function of range and azimuth. And this is how you get a SAR image, how you can simulate a SAR image based on this target. We did something similar with the last code. You remember that we generated the signal for a single target and then we integrated over all targets. This is exactly the same. And this is super fast. You know why? Mathematically, what is this? Fourier, no.
A is another.
A is, well,
Yes.
what else can it be?
Yes, it is another.
A is a matrix which is representing the intensity of your target in range and azimuth. Okay.
It's separable.
It's separable, yes, absolutely. And so it is a cascade of two operations. And what is the name of this operation? So now I'm calling Prati and I will say that you need to see him again. Yeah? This is a convolution. Two convolutions. Let's take this multiplied by this first term. And then you do a first convolution in range and a second convolution in azimuth. The order is not important, of course, so you can do azimuth first, it doesn't change anything. So, this is a super fast method to simulate the focused SAR image. You don't need to simulate the acquisition system or to simulate or to focus the image yourself. As simple as that. And this is very important because, for example, there are tasks which do not require you to simulate a side acquisition system. Maybe you just need to start from here. If you like, when we were playing with one-dimensional signal, we say that the most basic implementation would be to simulate the signal before matched filtering. But if you don't need to do that, you can also simulate the signal after matched filtering. So as long as you know what you're doing, everything is fine. And this is the same. This is one more step ahead. We can simulate a two-dimensional signal after focusing. Here it is. Now, what I want to talk to you about, which is very important, and I have time, is speckle. So last Monday, I did it a bit too fast, and I noticed that you did see something about speckle in the first part of this course, but not so much. Okay, there is no problem. So speckle in English is speckle, in Italian can be something like macchiette or macchioline, something of this kind. And it is a phenomenon that shows up inside images. Why? Mostly because of this term. Basically, what happens is, imagine, and this is something that you can simulate using this very simple approach. Imagine that you have a collection of targets, A, which you can imagine as a matrix of targets. So let's say that all of these targets have the same intensity. And so this matrix should be uniform, is uniform. Huh? But then imagine that the target position are not perfectly regular, meaning that do not imagine that in a grid like this, let's say that this is R and this is X. Right? So let's say that the target positions are not exactly in the center of your pixels. They can be a bit off. So like this one is here, the other one is there. So there is some randomness in this. Okay, and then the ingredient number 2, assume that the resolution of your SAS system is as large as many of these pixels. So let's say that your range and azimuth resolution is this one. Okay. So when you implement this convolution, then it means that you will form a new matrix such that each pixel of this new matrix is the result of 9 pixels here, right? Convolution. So for example, this 1 pixel will be the result of these 9 pixels here. This other pixel is the result of these other 9 pixels, and so on. Now tell me, we say that in the original image, all of these pixels have the same intensity. So this A is constant. Let's say that A is equal to 1 for each pixel. Can you tell me if the intensity here after this convolution is again constant or not? So this pixel here is the sum of these 9 pixels. This other pixel here is the sum of these other 9 pixels, right? All the pixels have the same amplitude. Do you think that the amplitude after convolution is constant? No. Of course it's not constant. You have the phase. You have the phase. We saw this when you have targets which you cannot resolve. So when you have 2 targets closer to each other than your resolution cell, then these 2 targets would sum up coherently, which means that their phase matters, and so they can even cancel out each other. And this is exactly what is happening. So each pixel here depends on the combination of all the phases here. So it is the sum, in this case, of 9 complex numbers. Say the first one with this phase, the other one with this other phase, then this phase again, and then this other phase. And so you get a random number here. Oh, well, let's say, is this phase really random? Well, let's assume that you have a wavelength on the order of centimeters, let's say 10 centimeters. Then, so a full phase cycle. So the phase is, So then the phase theta is 2 pi when r is half the wavelength. So it is just 5 centimeters, which means that if the randomness of this R0, so if the departure of this R0 from the center of the pixel is more than 5 centimeters, then your phase is a completely random number. You can have whatever phase. If your phase is random, then also the intensity of after convolution is random. And what is the statistics of a random variable which is obtained as the sum of many other independent random variables? it is Gaussian, of course. And so the pixel in your SAR image will be a Gaussian random variable. It will be zero mean, because in this coherent sum you can either have additions or cancellations, and so in the average you just get zero. And well, in this case there is no correlation between the real and the imaginary part, and so you can write this as a complex or circular Gaussian variables. You know this, no? CN, circular normal. It means that this is the ensemble of two random variables. One represents the real part of a number, the other the imaginary part, and we are assuming they are independent on each other. This you know it. Okay. The variance of this random variable will depend on A, and this is equal to the variance of A times the energy of these two cardinal signs. So let's say times a number which depends on these two. You can do the calculation. I'll let you this as an exercise. So, matter of fact, you, for example, take a photo of a beautiful grass field and you see it green, right? Then you take a SAR image of the same grass field, and you would imagine to see it uniform, because with your eyes or with your camera, you see it uniformly green. With the SAR, no. You just get one very white point and one dark point close to each other. Why? Because your pixel is a random variable. Okay? When you have a random variable, so if you would like to get a more stable result, so you would like to get rid of this variability, so what would you do?
I average. I take more pictures and I average.
Exactly. So the trick to get rid of this speckle, which is called despeckling in SAR jargon, is to take the absolute value of your image. Of course, the expected value of this one is your sigma squared, and you cannot, of course, take expectations, because you have not, or let's say, to mimic expectation with sample data, what you do is to compute the average of different sample data. So, for example, you can get rid of speckle by taking the average of the same image as collected at different times. So I just imagine that I take a SAR image of my grass field, then I take a different one, then another one, and so on. So I take 100 SAR images of my grass field, and I just take the average. This way, I am getting rid of this variability. Or what I can do, I can accept to sacrifice resolution, spatial resolution, and take the average in space. So I take the absolute value of this guy and I average it. So let's say I substitute this pixel for the average of the absolute values squared of these 9 pixels, or more than that, or these 15 pixels, oh no, 25 pixels, sorry. And so in this case, I am accepting to lose horizontal spatial resolution, but I get more stable results. Okay? A question for you. I can average different pixels, and this is clear to everyone, I think. When I said that I can average different images taken at different times, do you have any comment on that? Well, what is necessary for this approach to work? Well, let's say 2 things. The target has to be stationary, which means that they have to preserve the same intensity. Of course, if the field is burned, that there is no more gas field, and okay. But then you have to see different statistical realizations. Otherwise, it is exactly the same image, and there is no cancellation at all. I mean, you have to see a different speckle pattern, which means that you have to hope that the positions of your target within each, let's say that the position of each elementary target has changed by a fraction of the wavelength. Otherwise, you have exactly the same things, so you are just reproducing the very same acquisitions. For a grass field, this is most likely the case, because just for the width, you have motions.
But this is accomplished in a star system just because it's moving, right?
No, absolutely not.
We are saying
Absolutely not. I can mount a radar here and to image all of you. I just get a single number. This number that I get is the result of all the signal from any of you with the phase. Okay, so for any of you, I get an intensity and a phase, so a complex number. And I see the sum of all your complex numbers. Let's say that I am working with the radar at 10 gigahertz, so a wavelength of 3 centimeters. If you move by a fraction of these 3 centimeters, then the combination of all the complex number changes, and hence the amplitude changes. And so for example, I could mount a radar and say I go out. If I see the signal amplitude change, then some of you has moved by a fraction of 3 centimeters, and I just know it. Okay, so this is due to the fact that when multiple targets contribute to the same pixel or to the same sample, then their phases add up together. And this is what creates speckle. Why there is no speckle in optical images? Or why there is no speckle in our eyes? How is that for you?
because it's the power.
We don't see the face with eyes.
Because we have 2 eyes. No,
We do have 2 eyes.
just because we move our heads, we remove the face.
Because the wavelength is
I can do like this.
You already
It's
see an
only spec.
orange.
I see no speckle.
But for the
I'm
steering
not
wheel-
moving my head and I'm
Ah.
just using one eye. I see no speckle. Huh? So this is not the answer.
Because the wavelength is very, very low.
Hence we should have more speckle. We say that motions on the order of a fraction of a wavelength create speckle. So the shorter the wavelength, shorter wavelength, more speckle. Huh? We are not sensitive to the phase, but the power that our eyes are sensitive to is anyhow created by this coherent summation of phases. Hence, the physics is sensitive to the phase. So it doesn't matter if we don't see the phase, but physics does. Okay. So the thing is that optical imaging is very large bandwidth. It is a very large bandwidth thing. And matter of fact, our eyes, I mean, the way we see, you know, RGB, no? When we, so R, red, green, and blue is a technology to show color images in, say, in TV or computer monitor, or let's say in digital media. But RGB is also, by and large, the band of wavelength to which the cones in our eyes are sensitive to. So you know that we see in colors because we have different cones in our eyes, and so more or less one is sensitive. So one type of cone is sensitive to red, the other type of cone is sensitive to green, and then we have a third type which is sensitive to blue. What we see as a single color is the, oh, and this is frequency, yeah? Sure. So when we see red, we see, as a matter of fact, the integral done by the cone which is sensitive to red, done over a band of frequencies. So the things that we are already integrating, and when we integrate power. So we are integrating the power over multiple frequencies. And this is what is killing speckle. So our eyes are already implementing a despeckling system. They don't do this in time, they don't do this in space, they do this in the frequency domain. And so red is the integral of the power perceived by this kind of cones over a certain band. This is red, this is green, this is blue. So speckle is physics. If you want to get rid of speckle, then you have to have a system which implements some trick, like a very sophisticated signal processing method or a more sophisticated biophysical method, like our eyes. Just as a curiosity, I read in some studies that it seems like some humans have the fourth type of cones, which is more sensitive to particle effect. And it seems like that only women can have these capabilities. So very few women can have a fourth type of cones. Okay, so this is it. This is it. I think it's better if now I project something, because since we are talking on speckle now, it's better if we just see a speckle simulation. By the way, you can see speckle at optical frequencies. If you see images produced by a single tone laser system. So in that case, the bandwidth of the laser is very narrow, and you see speckle. Not as bright as usual. There you go. So here is your directory. This is a really simple simulation. I didn't prepare it just to be faster, but so this code, which is called Speckle, is a fast simulation of speckle effect on SAR images, and it is completely based on this fast way of simulating a SAR image by convolution. So what I do, I first create a backscatter map. So this is a matrix of 1000 by 1000 pixels, and just to make something that is easy to recognize, I divided this matrix in 4 quadrants, and in one intensity is 0, 1, 2, and 3. And so you have a sort of chess-like figure. And here is your backscatter map, so I can just show it, which is even easier. There you go. So this is the A variable according to the terminology seen before. Then SAR parameters. I'm just interested in a very fast simulation. So all I need is that the all I need to know is the range and azimuth resolution. Of course, for this simulation to make sense, I have to require that the SAR resolution is coarser than the pixel size in the original image, otherwise I'm just cheating. So I just say that it is 4 times as large in X and R. This is the axis of the filters. and I am using here a Gaussian filter for no reason. I could as well use a cardinal sign. I can use a cardinal sign if you like. So let's see. Well, because it is show. That's okay. So this way it's except. Let's make it larger. Larger. This is the length of the filter, right? So, haha.
That's why I got sync why.
Sync of what? What is
Why?
the problem?
Why is no underscore so
Ah, no, wait. Ah, right, sorry. Why did I take Y? Okay. So you can see this is my range filter, so it's the cardinal sign, and this is my azimuth filter. Another cardinal sign. Now, I am considering here two different cases. So the first case I'm showing you, which is case 2, is where I am assuming that the amplitude of each target is deterministic, so it's just the number I just show you in the backscatter map, but their phase is random. So this exponential phase here is playing the role of these terms that we discussed before. Here you look. So this is the backscatter map. So this is the first matrix I created. Then, based on this, I generated this new matrix called A, which is exactly the A behind the curtain here. And in this case, I am requiring that only the phase of A changes is random, whereas its amplitude is deterministic, and so since this is just the amplitude, there is no difference at all here. This is your SAR image. And you see it's, well, black is black, because if you integrate 0, you just get 0. But if the amplitude is different from 0, then you see all these speckles. You see this? Maquette. You see all these speckles here. And it is even difficult to notice that these two are two different intensities. It is very clear here, but the disturbance, so this random variation is so strong that you just cannot see it here, or it is very difficult to see it. So a very simple, so let's say the most simple approach, the most simple approach to stabilize this result is to perform some local filtering. So I take the absolute value of this guy and I just average it. So you see that I am losing spatial resolution, but at least I can distinguish different colors. Then it is also interesting to take a look at the statistics. So I'm considering here a single quadrant of the XR image, and I want to compute the probability density function of the real and the imaginary part of my XR pixels, and I can just do this with the histogram function, and then it is normalized such that the sum multiplied by the x or the y is 1, and then I just compare it against the theoretical DDP. And so you see here in blue it is the sample density probability function, so the one that I am measuring with the histogram function. In black there is my theoretical derivation, so this is a Gaussian function with a zero mean and whose variance is given by the variance of A multiplied by the energy of the filters. And so you see that even if the targets are constant in amplitude, then the statistics of the single pixel is Gaussian. And this is how, so this is the energy this is still in Italian, okay. Let's say normalization. Of backscatter. Maybe a comment on this is required. I call the energy, so we say that the pulse response is the product of two cardinal signs, so one in range and the other in azimuth, and I call the energy the effective area covered by the SAR resolution cell. Do you remember when we were treating one-dimensional signal and we say that I consider the pulse as being unitless, so that its energy represents the effective observation time? Do you remember that? Yes. Okay. This is exactly the same. So I know that a single target will induce this kind of signal. So I can imagine that these two are unitless, so that they, and since they are function of space, then their energy represents the effective area of the resolution cell. Is that clear? It should be clear. Back to monodimensional signal. We say that we have that S of t equal to some g of t minus tau, right? And we say that consider this unitless. so that the energy of S represents the observation time. I mean the effective time, the effective duration of the time when the target is illuminated by the signal, right? So this is the time. So in this case, this is space. So we say that your SAR signal is, let's say, GDR times GDX. So the energy of this one is, so the energy of GR is the effective length in range of the SAR resolution cell. The energy of GX is the effective length in azimuth, and so the product of their energy is just the effective area of the SAR resolution cell. This is why I am calling this area. Okay, so this is it for speckle. Another effect, and well, at this point I can go back to the slides, which at this point will be more clear. Dropbox. Where are you? Here. There we go. Speckle. We say when multiple targets enter in the same resolution cell, then you have an integration with phase, which creates interferences among the different targets, which creates speckle. This is speckle in a real SAR image. You see this black and white pattern. And this is speckle and this is the statistics of speckle. We say it is Gaussian circular, zero mean with some variance. If you remember, the variance of the squared absolute value of a complex Gaussian variable is the variance is the squared variance. So this is an information that you can use to see to what extent you are reducing this speckle by local averaging. And this is exactly what we have just did. This is an example from a real SAR image. So this is the more difficult to read because of speckle, and this is after a local average. And this is instead the same thing, but by averaging multiple images from different acquisition types. Yeah? So this is how you get rid of speckle. I would also like to show you a very simple simulation concerning geometrical distortion. And so we say that, so this is the slide. So we say that with a real, oops, I did something bad. Okay. So we say that a fundamental difference with respect to optical imaging is that one coordinate is represented by the distance from the instrument, which means that if you are, for example, acquiring from here, so your radar is up there and is looking at the scene from here, then you have a geometrical deformation, because the correspondence between ground range, so between the Cartesian coordinate we are so used to, and distance is not linear. And so the way you see, especially topographic variation in a SAR image, is non-linear. So what happens? For example, this is, let's say that this is a mountain or something similar. You see that, for example, these 2 points, so this D and H, they fall at the same distance. No, it says D and G. Okay, these D and G fall at the same distance from the radar. Okay, which means that they will be found in a SAR image at the same pixel. So these 2 parts of the mountain will collapse into the same pixel. On the other, how do you say for a mountain? If I say it, no. On the other side, it is the other way around. So, meaning that all these elements of the mountains fall at different range position, and so this means that this part of the mountain will take 1, 2, 3, 4, 5, 6 range pixels. This other part of the mountain will just fall in 2 range pixels, and so it is. So in the radar jargon, this is called foreshortening, meaning that all the whole side of the structure is appears to be shorter, and it can also collapse onto a single point. Now we saw some examples, but I think it's much easier to show you this other example, which is called geometrical, okay, with the short title, geometrical distortion. This is really elementary. I am just considering a flight height of 1,000 meters. This is the ground range coordinate. This is just the mean. And I am considering here 3 different scenarios. The first one is a mild topography. So this is a Gaussian function, so which is more or less the equation of a small field. And so this is my gentle topography. With these 2 simple lines, I am calculating the distance of each point from the radar. I write Ry because it is the distance as a function of the ground range coordinates. So it's R as a function of Y. And I just plot them. This is the topography as a function of ground range. This is topography as a function of range. Very good. You see we have this gentle topography here. The radar is at 0 and 1000, so the radar in this plot is more or less up there. You see here that this deformation is such that this side appears to be much shorter, whereas this other side is much longer. And this is called foreshortening, because the whole side of the mountain, of a hill or whatsoever, is shorter. you can push this further and assume a steeper slope. So for example, what happens if this hill is much higher? So in this case, the hill is 500 meters high, and you see what kind of distortion you have. So in this case, the closest point to the radar is the top of the hill. And so this is the point at the shortest distance. You have a phenomenon which is called layover, which means that at the same distance you have returns from two different pixels. Because, for example, so we say this is the shortest, and so for example this point, so this point and this other point are, so it goes like that, this way. Okay, so for example, this point and these other points are at the same distance from the radar, and so they fall at the same range position. There is nothing to do with that. We say that this is two-dimensional imaging. The world is 3D. We are just producing an image. So this is what we lose. So in some cases, we are just bound to squeeze two dimensions in one. This is it. This is the typical case of buildings. So the equation of a building is a rectangular pulsar, as simple as that. And here is it. This is your building in ground range, and this is how it appears in your SAR image. And so you have, of course, this. So the top is the first, is the closest point, and then you have the base here. Notice that what we are not considering here is that you also have another phenomenon which is called shadowing, which means that if this is a metallic structure, then there is very good chance that the wave is passing through. And so if we see this facet, then we will not see these other facets. And so at this point, with this simple code in mind, it should be easy for you now to tell me where is the flight direction of the radar here. This way, of course. So this is range. And this point is, so the top of the tower is the closest point. And so the radar is for sure flying this way, or this other way, but in this direction. And okay, so this is a very clear example. And what about here? What is the flight direction here? On the top, exactly, because you see this is the Vesuvio, so it is more or less symmetric, but you see that this side is much shorter than this other side, which appears to be much longer. So for sure, we are flying this way. Okay, so. I think for today this is it. You have, wait a sec, you have, I put different codes in your Dropbox folder. Airborne radar is the same as radar aereo, but with comments in English. So sorry for being so late. This is the code that we developed last Thursday with you, and this is the same but with some comments and some questions for you, and also a comparison with a more sophisticated focusing technique which will be discussed on Thursday. So take a look at that. Geometrical distortion is what we have just seen, speckle is what we have just seen. There is a full simulation of a synthetic aperture radar system which will be discussed on Thursday. Don't miss the next class because we will present the next homework. So see you on Thursday.